Question number 1 begins with the IV characteristic, that is voltage potential difference against current graph for a slice of semiconducting material. Part AI asks us to define resistance. We know that V equals I current divided by R resistance, so we can rearrange that. That would give us resistance equals voltage divided by current. This is a defined question in our exam papers. Defined questions will almost always be answered with some sort of word equation. In this case, we can say that resistance is potential difference divided by current. Part II asks us to show that the resistance of the slice is around about 250 ohms when there's a current of 40 milliamps in it. So if we have a look at our current axis here, the y-axis, where we have 40 milliamps, we can draw a line across and then draw a line down, and we'll see that the voltage is 10 volts. So we can now plug that into our equation for resistance. So R equals voltage, 10 volts, divided by, now you've got to be really careful here, this is the most common mistake with this question, is that students use 40 here when it should be 40 times 10 to the minus 3, because it is milliamps. So 40 times 10 to the minus 3, and that will give us our answer of 250 ohms. Part B now shows us that slice, and it shows us the dimensions of it. It asks us to calculate the resistivity, using the symbol ρ there, of the semiconducting material when there is a current of 40 milliamps in the slice. Now we know from the previous question that when the current is 40 milliamps, the resistance is 250 ohms. And we're going to use an equation here from the formula sheet that R equals rho L divided by A, and we're going to rearrange that. So we get the resistivity rho equals R A divided by L. Now the first things we need to work out here, what are our areas and lengths. So the current is flowing through this way, that means the length is this dimension along here, which we can see here is 1.5 times 10 to the minus 2 meters. And our cross-sectional area is going to be this dimension here, 1.2 times 10 to the minus 3 meters, multiplied by this dimension here, which is 1.5 times 10 to the minus 2 meters. So A equals 1.2 times 10 to the minus 3 multiplied by 1.5 times 10 to the minus 2, which gives us 1.8 times 10 to the minus 5 meters squared. So we can now plug all of those numbers into our equation. 250 ohms multiplied by 1.8 times 10 to the minus 5 divided by 1.5 times 10 to the minus 2. That gives us 0.3 ohm meters. Part C is a very tricky question. It says explain how the IV characteristic here shows that the resistivity of the semiconducting material decreases with increasing temperature. And we should explain how you are aware that the temperature of the slice changes. So first thing to look at here is that the graph is curving. So that means that the R resistance is changing. Now, in which way is it changing? Is it getting smaller as the voltage increases, or is it getting larger? Well, we can see from the curve of the graph here that the current is increasing at a faster rate than the voltage. which means that R is decreasing therefore, because R is proportional to rho, the resistivity is also decreasing. So that explains how the IV characteristic shows that the resistivity is decreasing with increasing current. We now need to link that to temperature. So we should be able to see that a higher current leads to a higher temperature. And if we like, we can refer to the power dissipation equation here. Power, so that the heat emitted from the semiconductor is equal to I squared R. So P is proportional to I squared. Hence the higher temperature when we have a higher current.